Okay, today we're going to be going over 6.6, the multiplication rule for AND. Okay, our learning target, I can calculate probabilities for multiple events, whether dependent or independent. Okay, that should sound familiar because in 6.1 we went over dependent and independent events. We talked about how dependent events, one event affected the other event, and an independent event, one event did not affect the outcome of another event, okay? So before we go into probability of compound events, I do want to jump back into the notes from last time, the 6.5, just to go over when we were doing OR probabilities, what we were doing is we were adding our two probabilities together. So when we think of an OR probability, you want to think addition, right? OR is add. Okay, sometimes we did have to minus something extra, but for the most part, we were adding when we think OR. Okay, jumping back into the AND probabilities, when we think of an AND probability, I want to think about multiplying, okay? So AND is multiplication and OR is addition, okay? So if we look at the probability of an independent event, the probability of A and B is just the probability of A times the probability of B, okay? So AND is multiply. That's when we have an independent event, or one event doesn't affect the other event. Now if we look at dependent events, the probability of A and B is the probability of A times the probability of B given A, okay? So this little line here is read as given. B given A. Okay, so what does that mean? It says in the above, the probability of B given A means the new adjusted probability of B happening if we know A already happened, okay? So that's the difference between these. In an independent event, you're just multiplying the two probabilities together, but in a dependent event, you have to take into account that, hey, my probability is changing, so I'm not just going to multiply the two probabilities. I have to change my next probability, okay? So that's a lot of information thrown at you. Let's look at some examples, make some sense of some of this, okay? So it says, determine whether the problem involves independent or dependent events, then find the probability, okay? Example 1, in a standard deck of 52 cards, if you pull a random card, what is the probability of pulling a diamond given it's a non-face card? Okay, so my first question, is this independent or is this dependent? Well, a big clue here is this. It has a probability of diamond given it's a non-face card. Okay, well, if I look back at my two events, the only one with this P given A right here is a dependent event. So this first is an example of a dependent event. Okay, so how exactly do I do the math with this dependent or this probability of diamond given non-face? Well, what I'm going to do is I'm going to set up a probability. My numerator, or my top number, is going to be the probability of both of these. So diamond and non-face card, okay? So I'm going to put that on the top of my fraction, and then on the bottom of my fraction, I'm just going to put the second item, okay? So I'm just going to put non-face card. Okay, now I got to figure out what these numbers are. So I have to think, how many diamond non-face cards are there? Well, let's just focus on diamond for a second. There's 4 suits in a deck of cards. So if I do my 52 cards and I divide that by 4, that gives me that I have 13 diamonds, okay? So I'm going to put a little 13 above diamond. And now I'm not just looking for the diamonds. I have to choose only the diamonds that are both a diamond and a non-face card. Well, how many face cards are there? In a deck of cards, the jack, queen, and king are all face cards, okay? So that's 3 face cards per suit. So if I take away my 3 face cards, that's going to leave me with only the cards that are a diamond and a non-face card. So in other words, 10. Okay, now I have to do my non-face cards. Another way to think about this is my total non-face cards, okay? So how many total non-face cards do I have? Well, if I have 10 face cards per suit, and there's 4 suits in a deck of cards, I can do 10 times 4, and that'll give me 40. So I have 40 non-face cards. If I simplify this down, I have 1 over 4 as my probability. Okay? Now looking at number 2, if you have 15 marbles in a bag, there are 3 yellow, 4 red, 5 blue, and 3 orange. If you pull 2 marbles at random without replacing the first, what is the probability of pulling a red and then pulling a blue? Okay, so let's take this one step at a time. First, we have to decide, are we independent or dependent? Okay, well, my biggest hint here is I'm pulling 2 marbles out and I'm not replacing them. Okay, without replacement, that's our indicator that we are in a dependent event. Okay, so if I'm looking at the probability of pulling a red out, okay, well, I have 4 reds, right? I'm going to put that over my total amount of marbles, which is 15. And I'm doing an and, so I'm going to multiply that by the probability of getting a blue marble now, okay? So I have 5 blue marbles, so I'm going to put that on top. But this is going to change because I've already pulled 1 marble out of my bag, okay? So now I don't have 15 marbles in my bag, I have 14 marbles in my bag, right? So I'm counting down because I pulled a marble out. If I multiply those fractions together, I get 2 over 21 as my probability. Okay, looking at example 3, if you flip a coin and roll a 6-sided die, what is the probability that you will flip a heads and roll an even number? Okay, well, am I independent or dependent here? Well, I've got to ask myself, does flipping a coin affect the outcome of me rolling a die? And the answer to that is no. It has nothing to do with the other. So I'm in an independent situation here. Okay, so if I look at the probability that I will flip a heads, okay, well, I know that I can get a heads or a tail. I have 2 outcomes, and only one of those is a heads. I'm doing an and, so I'm going to multiply. Okay, and now I want the probability that I will roll an even number. Okay, well, a die can give me 1, 2, 3, 4, 5, and 6, right? Out of those 6 numbers, how many of them are even? 2, 4, and 6, right? So 3 out of 6 are even. You can also write 1 over 2 if you reduce our fraction right here, whichever you prefer. Either way, when you multiply those together, you get 1/4. Okay? That's our final probability there. It says, in a bag, there are 5 blue blocks, 3 red blocks, 10 blue marbles, and 11 red marbles. If you pull an item at random from the bag, what is the probability of pulling a blue given it's a marble? Okay, so we're going to do this just like how we did it last time. Our numerator is going to be both of these together, so blue and marble. And my denominator is going to be just my second one, or marbles in this case, okay? But total marbles is what I'll put here because that makes me think about all of the marbles. Okay, so looking at the numerator, how many blue marbles do I have? Well, right here I've got 10 marbles that are blue. So I'm going to put a 10 right here. Okay. Now I need my total number of marbles. Well, I've got blocks here, blocks here. These are marbles, and these are marbles. So if I add my 10 to my 11, I get 21 total marbles, right? So my probability is 10 over 21. Okay, we did skip over whether this was independent or dependent, but this one shouldn't be too hard because we have this probability of B given A, so we are in a dependent situation here. Okay, looking at example 5, in a standard deck of 52 cards, if you pull 2 cards at random, what is the probability of pulling a 3 and then pulling a face card? Okay, so are we independent or dependent? Okay, well, I'm pulling a card out, but it never says that I'm putting it back into the deck. Because I'm not putting it back into the deck, I am a dependent situation here, okay? If it had said with repeating or putting it back in the card, then I'd be independent, but for this, it didn't say any of that, so I'm dependent. Okay, so let's look at our probability of pulling a 3. How many 3s are there in a deck of cards? Well, just from experience, I know that there are 4 3s in a deck. 4 3s in a deck of cards. Another way you can think about that is there's 1 3 per suit, and we have 4 suits, so 1 times 4 is 4, right? Okay, and I've got 52 total cards, says right here. I'm in an AND probability, so I'm going to multiply. And now I need to find the probability of pulling a face card. Okay, well, if you remember on example 1, we said that there was a total of 40 non-face cards, okay? So we have 40 non-face cards. So if I take my total of 52 and I subtract those 40 non-face cards, that's going to give me, I have 12 face cards, right? So I'm going to use 12 as my top number here. Now, thinking about my denominator, I've already taken 1 card out of my deck of cards, and I did not put it back into the deck. So instead of 52 cards, I've got 51 cards. I have to count down because I already took a card out. Okay, if you multiply those together, you get 4 over 221 as your probability. Okay, example 6, if you select and keep 4 marbles randomly from a bag containing 5 yellow, 3 red, 10 green, and 12 orange, what is the probability that the first 2 will be yellow and the next 2 will be green? Okay, so am I independent or dependent here? I'm pulling 4 marbles out of the bag, and it never says I'm putting them back in the bag. So again, I'm going to be dependent, okay? So I want the probability of the first 2 being yellow, okay? So how many yellow do I have? I have 5 yellow. So I'm going to do, for my first fraction here, 5 over my total. Well, this one actually doesn't give us our total, right? So we have to find it. So to find our total, I'm going to add 5 plus my 3 red plus my 10 green plus my 12 orange. Okay, and that's going to give me 30 total marbles. So 5 over 30 is the probability of pulling a yellow out my first time around. And then I'm going to multiply that by the probability of pulling another yellow out, because I want my first 2 marbles to be yellow. But I no longer have 5 yellow marbles in my bag because I already took 1 of them out. So I only have 4 yellow marbles in my bag. Because I already took that 1 yellow marble out, I also don't have 30 marbles in my bag. I have 29 marbles in my bag now. Okay, so I'm counting down on both of those because I already took 1 yellow marble out. So I have to account for that on both the top and the bottom of my fraction. Okay, now I want the next 2 marbles to be green. Okay, well, I have 10 green marbles, so I'm going to pull 10, or I have a chance to pull 10 of them out of how many? Well, I've now taken 2 marbles out, so now I have 28 marbles in my bag. Okay, now I want to pull 1 more green out. Well, I no longer have 10 green in there. I only have 9 green in there. And I'm going to put that over 27 because now I've taken 3 out already, right? 1, 2, 3. So 27. Right, if we multiply all this together, we get 5 over 1,827. But this question asks us to put it as a percent rounded to the nearest hundredth. So I want a decimal answer, so that's about 0.0027. And if I'm going to make that into a percent, I'm going to move my decimal over 2 spots. So I'm going to have 0.27%. And I'm going to leave the percent sign off because Delta Math doesn't like the percent sign, but normally I would put a percent sign there. Okay, so we are going to skip number 7, skip number 8, and skip number 9. We're going to jump to the next page here. All of these are going to be examples pulled straight from Delta Math, so this should help with your homework. And this is also exactly what your quiz is going to look like next class, okay? So in a certain Algebra 2 class, of 29 students, 13 of them play basketball and 14 of them play baseball. There are 10 students who play neither sport. What is the probability that a student chosen randomly from a class plays both basketball and baseball? Okay, so we want to know those who play both sports. We want to know who plays basketball and baseball, right? The overlap. Well, if you remember from last time's notes, I think it was the last question, we found how to find our overlap, right? So how we did that was we set 29, or our total amount, we set that equal to all the other numbers added together. So 13 plus 14 plus 10. Okay? So if it equaled the same number, then there's no overlap. But if it doesn't equal the same number, like this one, 13 plus 14 plus 10 gives me 37, then we know that there's an overlap, okay? So because those don't equal the same number, I know I have an overlap, which is good because it's asking for my overlap. So I hope I have an overlap, right? Okay, but then once we found out these numbers, we took our number that we found, 37, and we subtracted that from our total that we're given. Okay, so 37 minus 29 gives us 8 who play both. So our probability here is going to be 8 over 29. And that's the overlap that we're looking for. Okay, there's a spinner with 12 equal areas numbered 1 through 12. If the spinner is spun one time, what is the probability that the result is a multiple of 3 and a multiple of 4? So I'm going to write down my numbers 1 through 12. Okay, and I'm looking for my multiples of 3 and my multiples of 4. So I'm going to label my multiples of 3A and my multiples of 4B. Now I'm just going to count by 3s, and everywhere that I stay, I'm going to put an A. So 3, 6, 9, and 12. Now I'm going to count by my multiples of 4, and I'll put a B everywhere there. So 4, 8, and 12. Okay, now the question is asking for the numbers that represent both a multiple 3 and a multiple 4. So what numbers have both an A and a B next to them? And that's just our 12 here, right? So we can say that we have 1 out of 12 of our numbers. Okay, so the next example says in a certain Algebra 2 class of 20 students, 5 of them play basketball and 6 of them play baseball. There are 2 students who play both sports. What is the probability that a student chosen randomly from a class plays basketball or baseball? Okay, so we're not doing an and problem anymore. We're doing an or problem, right? Okay, so this is going to be like 6.5, okay? We are going to want to find the probability of those who play basketball, then add that to the probability of those who play baseball, and if they share any in common, then we will subtract those, okay? So just looking at basketball, how many students play basketball? 5 of the students play basketball, okay? So 5 of my 20 students, and I'm in an or problem, so I'm going to add. And now baseball, how many play baseball? 6 of them play baseball. Okay, so 6 over 20. And now I have to see, do they have any overlap? Okay, well, it says 2 students play both sports. So now I will subtract my 2 students who play both. 5 plus 6 minus 2 gives me 9 over 20 as my probability. Okay? So it says there is a spinner with 9 equal areas numbered 1 through 9. If the spinner is spun 1 time, what is the probability that the result is a multiple of 2 or a multiple of 3? Okay, so am I in an and or an or? I'm in a or, right? So or is add, okay? So my multiples of 2, I'm going to label A. That's not right. I'm going to label A. And my multiples of 3, I'm going to label B. Now I've got to number all my numbers 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. I'm going to put an A under all my multiples of 2. So 2, 4, 6, 8. And a B under all my multiples of 3. B is 3, 6, and 9. Okay. So now looking at just my A's, I have 1, 2, 3, 4 A's. So 4 over my 9 numbers. I'm going to add, because I'm in or, that to my 1, 2, 3 B's. Okay. And now I have to subtract anything I share. So is there a number that has both an A and a B? 6, right? Okay. So I'm going to circle that green. I'm going to subtract 1 out of 9 because I have one number that has both an A and a B. So that gives me 6 over 9, or if we simplify, 2 over 3. Okay? All right. So these ones can be a little bit tricky. You really have to pay attention to the words here, okay? In a class of students, the following data table summarizes how many students have a cat or a dog. What is the probability that a student who does not have a dog has a cat, okay? So this one's not asking for the probability of the whole class. It's asking out of the students who don't have a dog, how many of them have a cat, okay? So when it's worded like this, it's worded backwards, okay? So another way to look at this is I'm going to say P of, and I said it was backwards, so this one's going to go first, okay? The probability that they have a cat given, and now this one's going to go second, okay? Given that they do not have a dog, or no dog is what I'm going to say, okay? So now this looks a little familiar. So I can say that what goes on top is having a cat and not having a dog, okay? So that's going to be my top, has cat and no dog. Then what will go on my bottom will be just the probability of not having a dog. So total of no dogs. Okay. Well, if I look at my table, I need has cat and no dog. So has cat matched with no dog is 11. So I've got 11 who have a cat but no dog. And now I need to find the total amount of people with no dogs. So does not have dog is 11 plus 9, okay? So I'll do 11 plus 9, which gives me 20. Or in other words, I've got 11 over 20 as my probability, okay? So that one's worded weird. It's worded backwards. When you set it up like this, you have to make sure you put the first one second and the second one first. But sometimes it might say something like, what is the probability that a student who has a cat given they do not have a dog? If it says given, then you'll just do it in order. So if this were to say given, this would be my first one, and this is my second one. But this one does not say given, so I have to switch them. Okay, so that might come up on Delta Math, so just make sure we're looking out for that. Okay, looking at a similar one. In a class of students, the following data table summarizes the amount of sleep students and whether they have an A in the class. What is the probability that a student chosen at randomly from the class is a student who slept 6 hours or less, does not have an A? Okay, so that's worded weird as well, okay? But I'm looking for what's my total here. Last time my total was just the students who do not have dogs, okay? This time my total is from the class, okay? So now the entire class is going to be my total. So what I'm going to do is I'm going to take 7 plus 4 plus 5 plus 14, and that's going to give me 30. Now 30 is going to be my denominator here, okay? That's because it says I'm taking it from the class, not from a specific subset of students, okay? Now I'm looking for those who slept 6 hours or less and does not have an A. Okay, so I'm looking for the intersection of slept 6 hours or less and does not have an A. Well, those intersect right here at 14, okay? So that will be my numerator here, 14. Those are who slept 6 hours or less and who does not have an A. So my probability will be 14 over 30, or if we simplify this down, 7 over 15. Okay, last one. A survey stopped men and women at random to ask them where they purchased groceries at a local grocery store or online. Okay, how many men surveyed shop online? Well, if I look at men and I look at shop online, where do they intersect? Right here at 7. So I have 7 men who surveyed shop online. Doesn't ask for a probability or anything, so that's my answer, 7. Okay, so there's Delta Math. Remember, this is exactly like your quiz, so pay attention, fill out your yellow note card, and be ready for the quiz next time. Thanks.